Hello everyone. In this video we will see the idea of grayscale morphology. So far we had looked at the morphological image processing applied on binary images. We have seen several operations such as dilation, erosion, opening and closing, and some extension of that in the terms of geodesic dilation and geodesic erosion, and we had seen some reconstruction using those techniques. Now we will see how we can apply the morphological techniques on grayscale images. Okay, the idea of grayscale images is quite different because the images in the image can differ from 0 to 255 if we are using 8-bit integer representation. But in the case of binary image, you had only two values, 0 and 1. But in the case of binary images, we took the images as sets, but it is not like this in the case of grayscale morphology. In the case of grayscale morphology, we are treating the images as a digital function f of xy, and also we are taking the structuring element also as a grayscale counterpart of the binary structuring element. So here also we are treating both the image as well as the structuring elements as grayscale images. So this is my image and this is the structuring element that I'm going to use. As we know, the purpose of using a structuring element is to examine or to extract the properties that we are looking in an image. And in the case of this particular structuring element, when it comes to grayscale morphology, we can have two different structures. That is, the first one is a non-flat structuring element and the second one is a flat structuring element. Okay, so these are two different types of structuring elements that we can use when you do morphological image processing on grayscale images. Okay, the difference between the non-flat structuring element and flat structuring element is quite clear from the diagram itself. The non-flat structuring element will use the different intensity values which are gradually increasing from its boundaries to the center. So if you take a cross section along this point, the intensities on the edges are very low, so you can see that over here, and the numbers are increasing when it comes to the center. The center we have the highest value, and it is reducing as you go from the center down below the edges. Now when it comes to flat structuring element, you do not have different values, you only have the highest possible value that is present in the image. So depending on whether the structuring element is flat or non-flat, we have different equations for finding the dilation or erosion operation of a grayscale image, which means that the equation will be different if you are using a non-flat structuring element or a flat structuring element. So in the discussion that follows, I will talk about both the cases. The first operation that we are going to look at is the erosion and dilation. Using a flat structuring element. Okay, so if you have an image f of xy, you have a structuring element which is a flat structuring element. I'm calling it as b of xy. Then the operation of erosion and dilation are defined as follows. So you have to remember that this is a flat structuring element. Okay, so the definition of erosion of the image f with a structuring element b, as this is a function of two independent variables x and y, this is the kind of notation that we are going to use. Now the definition is like this: you have to take the minimum value of the function f when you probe the neighborhood of f of x y. So this is the kind of definition that we are going to use. This is y in fact. Okay, now you have to do this process by changing the value of s and t for every coordinates of the structuring element. Okay, so to simplify this definition, what we are essentially doing is, suppose that this is your structuring element. Okay, suppose that I am using a 3 by 3 structuring element, and the actual value of this structuring element doesn't matter because we are actually using a flat structuring element. The intensity is not coming into this equation. Okay, Now suppose that this is your as I said, this is your structuring element. Let me call it as b of xy, and suppose that this is your image. Okay, now what we have to do is you have to take the center of the structuring element and you have to place it over every pixels of my image. Okay, suppose that I'm placing it over this pixel. Okay, the center of the structuring element is coinciding with the pixel that I'm doing the operation on right now. Then what we will do is we will look at all the neighborhood that is defined by the structuring element. Then we will take the minimum element among all those 9 values. So this is kind of a min filter. So if you want to make sense out of this equation, you have to take the center of this particular structuring element having coordinate 0 0, and this will be 0 1, this will be 0 minus 1, and so on. So when you take the 0 0, so when you take the center as with the coordinate 0 0, the value of s will be 0, t will be 0, so that is referring to this particular pixel, that is f of x y. Now if you are taking the coordinates at this pixel, that will be 0 and 1, and if you add 0 and 1 into this equation, then you will be referring to f of x comma y plus 1, so that will be referring to this pixel. So essentially you are defining a neighborhood by using the structuring element. Then you will be probing for all the values defined by the structuring element. Then you take out the minimum value, that will be the value that is going to replace this pixel. So if you do the entire operation over the image, then you will get the erosion operation or the grayscale erosion operation by using a flat structuring element on this image. So this is the equation that we are going to use. Now similarly for dilation, so the one that we had looked at is erosion. Okay, now we are going to look at dilation using a flat structuring element. Okay, so the definition of dilation goes like this. So you have an image f, then you are actually dilating it, so we are using a plus sign inside a circle. As this is a function of two independent quantities, I will be writing it like this, x comma y, and this is defined as, instead of min we will be using max, and we are taking every coordinates that correspond to the structuring element b. And so there is a small difference here. We are inverting the structuring element, or we are taking the mirror image of the structuring element before we operate. This is just like the convolution operation that we do on digital images. So f of x minus s comma y minus t, and you have to take all the values that is overlapped by the structuring element, or in other words the mirror image of the structuring element, then you pick out the highest value among that. Okay, so I will demonstrate it here with an example. So suppose that this is my image, and this is my structuring element. So as the first step, you have to invert it with the center. So as this is a symmetric structural element, so it doesn't make any difference. So you can take the center of this structuring element and you place it over every pixels of this image. Suppose that, for instance, I'm placing it at this point. So the structuring element will be overlapped just like this. Then you pick up the maximum value among all the neighborhood of this pixel, then replace this point with that maximum value. So this is kind of a max filter that we have already seen in the spatial filter, or a non-linear spatial filter. Okay, so this is how you do the dilation operation when you have a flat structuring element. This is the structuring element b of xy, and this is the image f of xy. Now we will look at the erosion and dilation for a non-flat structuring element. Okay, so the first equation is the equation for erosion. Okay, so when you look at this equation, this has a little bit change, unlike the flat structuring element. Here we are actually subtracting the intensity of the structuring element. So for a non-flat structuring element, we will have different values in the structuring element itself. So imagine that this is my structuring element. So there will be several different values for the structuring element itself, 1 2 3. So these values are some example values, 6 7 8 9. Assume that these are certain intensity values in the structuring element. So whenever you have an image, and when you overlap it over a, let me use another color, when you overlap it over the image pixels, suppose that the sender is at this point, so you have to find the, you have to take each of the intensities in the original image and you have to subtract these values from those intensities, then you find the minimum out of all those values in the neighborhood covered by the structuring element. Okay, and in the case of dilation, this is the equation for dilation. So in the case of dilation process, what you're doing is, if you have let's say value of S and T are, let's say 1 1, then you are actually referring to this particular point. If this is 0 0, and this will have the value of 1 1. So whenever you are referring to S and T as 1 1, and if the center is overlapped at this point, then you will be actually referring to a pixel which is f of x minus 1 and y minus 1. So this will be the pixels f of x minus 1 and y minus 1. Okay, or in other words, you are actually taking the 180-degree rotation of this particular structuring element, or you are taking the mirror image of this structuring element with respect to the origin, that is with respect to x and y axis, then making this as the sender, you will be overlapping it like this. Then you will add all the values of this f of xy and the neighborhood covered by the structuring element with the values of the structuring element which are flipped by 180 degree, then you will find the maximum out of it. So this is the equation for dilation when you are using a non-flat structuring element for the morphological image processing. Okay, usually the usage of non-flat structuring element are not that common, and I hope the process is clear. Thank you.